This is a live session where we'll be discussing some of the content that is covered in the course. So am I audible? Okay. Hope this will be an interactive session, so where we can have discussion regarding the problems as well. Okay, this is week 2 discussion of the fabrication techniques for MEMS based sensors from the clinical perspective. So I am the course TA Rayan Jasma. So I am a research scholar at IIC Bangalore, and I work in the field of piezoelectric MEMS resonators. So my live session will be held every week from every week on Monday from 6 to 8 p.m. So this week, before that, is my screen visible? So right now when I was talking, the screen was visible, right? The shared screen. Are you able to see the PPT?
Yes.
Okay. So some of the topics that were covered in the week 2 were silicon growth by Sokolsky process, silicon dioxide, both dry and wet oxidation, physical vapor deposition. In that, 3 techniques were covered: thermal evaporation, E-beam evaporation, sputtering. Then we also had some content on photolithography. So now we'll just move on into problems related to these topics. Okay. So first problem is Sokolsky method is ideal for A. Polysilicon to single crystal ingot, B. Polysilicon to prime grade silicon, C. Polysilicon to mechanical grade silicon, D. Mechanical grade to polysilicon. So what is the answer?
C.
1 minute. Yeah. So what is the answer?
I have a doubt between A and C. Looks like C. C is the answer.
Okay. So like in Sokolsky method we can get the answer is A, not C. I'll tell why. So like say mechanical grade silicon is like it can be used for there are different grades of silicon. So in that, mechanical grade is like you can use it to make mechanical structures like MEMS. It is good for that. But when you go on to transistors or other kind of circuit where the properties of silicon matter very much, we will not have we cannot use mechanical grade silicon. So if we see the Sokolsky process, like how it goes is in the first step, what we'll do is we'll melt silicon ingots, but these silicon ingots are 99.999 times percentage pure. So then we will introduce a seed crystal. So this seed crystal will have a particular orientation. So it may be 100 oriented or 110 oriented or even 111 oriented. Then we'll dip the seed crystal in the molten silicon. Then we'll start to rotate it slowly. So this seed crystal will be rotated in one direction, let's say, and the cylinder in which the melt is kept, that will be rotated in the opposite direction. So that's how the crystal pulling works. So once the silicon, so as we move up, what happens is the silicon melt will start to solidify. Since we are moving in a circular fashion, we will get this kind of cylindrical ingot. So whatever cylindrical ingot that we are getting will be very pure, and all the impurities that might have been present when we initially melted the silicon will be left as a residue in the melt. So like this process is used to prepare a very high quality silicon. So the answer is option A. Okay, so is this clear? Is this clear?
Yes, yes.
Okay. So also, let's say if we want a doped silicon wafer, we can add some doping materials as well in the molten silicon. So our final ingot will have the particular doped property. So we'll move on to the next question. For CZ method, here is Sokolsky method. The growth of which plane is more difficult? 100, 110, 111.
I'm just giving a guess as 111.
Okay. So are you aware of like what are these planes? 100, 111,
Yes, yes.
1. Okay. So like say silicon is an anisotropic material, right? So like its properties will vary depending on the orientation. So there are certain planes in the like there are certain planes defined in the silicon crystal such as 100, 110 and 111. So these planes can be represented like these are the Miller indices representation of the plane, and here you can see how the like atoms will look like when you see from this plane, right? And if say we want to draw the Miller indices of a particular plane 100, you can see the shaded portion here, right? So this is the 100 plane. How do we like find which plane it is referring to in the particular lattice? So let's say we have a lattice like this. So like we know that there are different orientations. Let's say if you want to know where the 100 orientation is, then what we will do is like we will have a different coordinate system associated with this lattice. So this is a unit lattice. So our main coordinate system, this can be x, this will be y, and this will be z, right? So if we want to draw 100 plane, what we will do is first we will have to this is the Miller indices of a plane. We will have to find the intercept of the plane with respect to the coordinate axis. So the intercept will be, let's say a, b and c are the Miller indices, then their intercepts will be 1 by a, 1 by b and 1 by c. So we will just take reciprocal of each of the terms. So this will be 1, infinity and infinity. So it will intersect the x at 1. It will intersect the x at 1, y at infinity and z at infinity. So it will be this plane. So this is how like we find out which plane is represented in the using the Miller indices. So like this we can say that the 110 plane it has intercepts of at 1 with both the x and y axis. 111 plane will have intercepts with both x, y and z axis at 1 position. So like the growth will depend on like what is the surface energy of this plane. So if the surface energy of the plane is less, then the growth will be more easier. If the surface energy of the plane is high, then the growth will be less. It will be like it will take time to grow. So if we consider these three planes, the surface energy of 111 is the lowest. Uh, sorry. The surface energy of 111 is the lowest. The surface energy of 110 is the highest. So this has the highest surface energy. This has the second highest surface energy, and this has the third highest surface energy. So if the surface energy is higher, then the growth will be easier. If the surface energy is low, then the growth will be faster. And also you'll come to know that that's why this 111 wafers are very expensive, because it is very difficult to grow them. So like say we have different wafers, right? 110, 100 wafer or 111 wafer. So in those wafers, if you are having a wafer like this, and this will be the normal that is coming out of the wafer, I mean, normal to the surface of the wafer. So this normal will be pointing along the direction, it will be pointing along the like 110 direction, crystallographic direction, and the wafer will be along this like whichever plane. So if it is along the 100 plane, then the surface of the wafer will be along the 100 plane. So this is how the wafers will be oriented with respect to the Miller indices system. Is this clear?
So 111 is difficult to grow as well as difficult to etch, right?
Yes.
Okay, yeah.
So we'll move on to next one. Why are single wafers circular, and what is the diameter of the ingot in the Czochralski method depends on?
Yeah, so maybe I would like to, I'll try to answer for this.
Yes.
First is because we put the seed and rotate it in a circular fashion, so maybe that is how it is circular. And the second is the diameter of the ingot in a CZ method is it 6-inch and 4-inch or something like that?
No, it can vary, like
Okay.
depending on like what kind of size we want and how long we pull, it will vary. Okay.
So general diameter is I have seen 6-inch if I'm right.
Okay. So like as we saw in the earlier slide, in Czochralski process, when we pull out the crystal, it comes out in form of a cylindrical ingot, right? Then what we do is we cut this cylindrical ingot into thin wafers. So that's how we get a circular wafer. And say in this in this type of fabrication process, it is a closed loop system. So where we will be supplying some amount of heat to this crucible in order to melt the silicon, and we will be maintaining it in some inert condition, because we don't want any impurities to be present when we are making the silicon ingot, as well as we don't want any reactions with oxide, any oxygen or nitrogen to happen. So like since it is a closed loop system, like the amount of heat that is given into the system minus the amount of heat that is taken out of the system will be equal to the latent heat of crystallization. So this is the equation that will govern the growth of the crystal. And here A is the area of the ingot, rho is the density of the silicon melt, L is the latent heat of recrystallization, and dx by dt is the rate at which we are pulling the seed crystal along with the crystal ingot up. So if we consider the diameter of the wafer, So we'll have to look into the area term, right? So that is proportional to the heat in minus heat out. So how much heat we are giving, and it is also inversely proportional to the rate of pulling. So if we pull faster, then we will get a like smaller diameter. So not just in like say if you are just pulling something in a circular fashion, if you are pulling faster, then it becomes more thin, right? And it is also inversely proportional to the density and also to the latent heat of recrystallization.
I just wanted to know what is the minimum speed and maximum speed possible here.
uh, I'm not sure about the exact values, but so that all depends on not just like it also depends on the heat and other parameters that are in the system. We cannot pull too fast. Let's say if we pull too fast, and it will also be limited by the so it is like you can say it is inversely proportional to the rate of pulling, right? So if we pull too fast, then we'll get very small diameter wafers. If we pull too slow, then we'll get very large wafers. But again, with larger wafers, we need to have higher thickness, because if we have very thin wafer with very large diameter, it may break easily, right? And also the size of the wafer should be compatible with whatever equipment we are using to process those wafers. Let's say our equipment can handle only maximum 6-inch wafer. Like industry standard equipments, if it can handle only 6-inch wafer max, then like there is no point in having a very like larger diameter wafers which cannot be sold commercially. So the speed will normally be limited by the diameter as well as the other parameters that come in with it. Is it clear?
Yeah, thank you.
So we'll move on to the next question. Right. Device reliability is important when fabricating devices for commercial use where long lifetime is required. However, reliability issues cannot be always determined immediately after fabrication. Which of the following failure modes that are originating from fabrication can be detected during or shortly after the fabrication of a device? So means reliability means we have to know when we fabricate a device, like whether it will work properly or not, right? So but there are some issues that can be determined after long period of operation. But like here in this question, we just have to find out which one can be detected during the fabrication process or immediately after the fabrication process. So option A is corrosion due to environmental humidity. B is strain induced stress causing failure by temperature variation. C is particle contamination. D is fatigue due to cyclic loading of a device.
Is there a single answer or
It's a single answer.
looking like all the answers are holding good?
No, like you have to find which which can be detected during the fabrication process or immediately after the fabrication process, not which one is a long time. Like which failure will occur immediately. Like you can find that some kind of failure has occurred immediately during the fabrication process or after that.
I have a doubt between the strain induced stress causing the failure or the particle contamination.
Okay. So the answer is particle contamination, like strain induced stress by temperature variation. So this one can occur when you are subjecting, let's say you have made a mechanical device, you are subjecting the device, MEMS device, so which has some mechanical parts, you are subjecting the device to some temperature variation. Because of that there is some stress and like some strain induced in the structure, which is causing it to like not perform as well, like buckling or like it may get deformed under the stress. So if something like that is happening, then we can say that as strain induced stress. But normally whatever fabrication process we do, that will not have like it will not be subjected to that much temperature variations, right? So in the process of fabrication we may have temperature variation, but the performance of, like, we cannot say that the device has failed due to temperature variations. But particle contamination is one which we can easily find out. The reason is, like, there are different types of particle contamination. So some of them are ionic materials, molecular compounds, elemental particles, and airborne dust. And also you would have known that, like, in clean room, we fabricate the devices in a clean room environment where we have like a system to control the amount of particles inside. So the reason is that these particles will interfere with whatever devices we fabricate, and will the devices that we fabricate will not have our desired performance. So this is also one of the reason why they do a gowning procedure in order to enter a clean room, so that, like, when we go inside the clean room also we do not generate much particles which will affect our fabrication processes. So here you can see some like examples of contamination, particle contamination, metallic contamination, and so on, and their influence on device characteristics. So like, if our devices are like transistor based devices, or like depending on the semiconductor property, if they depend on those things, then like they are very sensitive to this contamination. So when we do processing, we should ensure that there is no contamination that is happening. So like, say when we are fabricating the device, during the process of fabrication or immediately after fabrication, when we test, we'll come to know whether the device is performing as our desired expectation, or there is some contamination which has caused the device to not like work as intended. So is this like, have you understood this?
Yeah.
Okay. So now we'll move on to the next question. So this question is based on oxidation. Oxide films of 750 nanometer are grown on silicon wafer by both dry oxidation and wet oxidation process. The thickness of silicon wafer consumed in dry oxidation and wet oxidation are as follows. So we have 4 options. In the first option, it is 150 nanometer both. In the second option, it is 345 nanometer for both cases. In the third option, it is 115 nanometer for the first case, 345 nanometer for the second case. And in the fourth option, it is 345 nanometer for the first case and 115 nanometer for the second case.
I would like to just guess that usually dry oxidation will have lesser thickness and wet oxidation will have more thickness. So would like to go for C option.
First I'll just tell. So what happens in an oxidation process, like whether it is dry or wet? In the case of dry oxidation, the silicon will react with oxygen to form silicon dioxide, whereas in the case of wet oxidation, it will react with water to form silicon dioxide and hydrogen. One important thing to note here is that this reaction will happen at the surface of the wafer. So if we are having a silicon wafer, at the surface the reaction will happen. So let's say we have some thin layer of silicon dioxide, like few nanometers thin, then the oxygen or water from the environment will have to diffuse through this layer, reach the silicon layer, and then it will react with the silicon on the at the interface, and then it will form oxide. So oxide will, let's say it will start growing inward. So it will consume some amount of silicon. Whether it is wet or dry, like the quality may be better in one of the cases, but like the process by which the oxidation happens is the same for both. So there is like, say if we are having a silicon wafer, after oxidation the silicon dioxide like it will expand in upward direction as well, but it would have expand inside through the silicon as well. So like there is a pill with pilling Bedworth ratio, which is used to determine how much silicon is consumed for a particular amount of thickness of silicon dioxide. So it is given by the ratio of the molar volume of the silicon dioxide to the ratio of the molar volume of the silicon. So silicon dioxide molar volume is 27.19 and for silicon it is 12.40. So the ratio becomes 2.19. If we take the inverse of that, it is like it is also equal to 0.46. So what it means is, let's say we have 1 micron of SiO2, then 460 nanometer of silicon would have been consumed. So is this understandable?
Yes.
So like in our question, we have an oxide film of 750 nanometer. So here what we have to do is we just have to substitute the value. So here we'll have 750 divided by silicon thickness equal to 1 by 0.46. So if we multiply this, we'll get silicon thickness of close to 350 nanometer for both the cases. So this pilling Bedworth ratio is not only applicable for silicon, but also for like certain metal oxide growth as well. Like we have the same like similar equation. The values will be different depending on what metal oxide and what metal is present. So the answer for this question is B, 345 nanometer, 345 nanometer. Is this clear? Any doubts?
Yeah.
So now we'll move on to the next question. Why is vacuum created in the chamber before thermal evaporation? So you would have learnt about thermal evaporation, right? A, to increase the mean free path of the evaporated molecules. B, to get a film with more purity. C, to prevent oxidation of evaporated materials. D, all of this.
D, all of this.
Yes. So so this is the answer is correct. The correct answer is D, all of this. So we have various pressure ranges. So if it is between 10 bar 1 bar to 10 millibar, then we call it as low vacuum. If it is between 10 millibar to 10 bar minus 3 millibar, it is medium vacuum. Then we have high vacuum as well as ultra high vacuum. So like our deposition process for evaporation will happen mainly between in the medium vacuum. So this is 10 power minus 5. So it will happen in the medium vacuum range. So there is if we see the option B, we need a film with more purity. So what does this mean is, like when we are evaporating the metal, it should not react with any of the ambient that is present inside the chamber. So if it is not in vacuum condition, there may be some oxygen or nitrogen present, which may react with the metal which is thermally evaporated. As the thermally evaporated metals, they can easily react to form any oxide or nitrate. So we need an ambient where there is no other unwanted material, and also we want to prevent the oxidation of evaporated material. Let's say if there is oxygen in the evaporator, then it will react with the evaporated material and it will deposit oxide instead of depositing the metal that we want. Then there is also option A, where we have to increase the mean free path of the evaporated molecules. So what is mean free path is? Mean free path is the time taken between two collisions. So let's say if we are having the chamber in atmospheric condition, then we'll have many number of particles inside. So whatever are evaporated molecules, it will easily collide with any of these particles present. So the mean free path will be very less in this case. But if we have an evacuated chamber, then in that case the number of particles will be less. So there will be minimum interactions between the unwanted particles and the evaporated molecules, and it can easily reach the target. So we have in most of our deposition systems, we'll have vacuum in order to increase the mean free path as well. So to increase the time between two collisions, also to get a film with more purity and to prevent oxidation of evaporated materials. So the answer is option D. Is this clear?
Okay.
Any doubts?
I understood.
Okay. So next, ALD can be used to deposit a film with minimum thickness and better precision. True or false? So here ALD is atomic layer deposition.
Yeah, I would go for true.
Okay. So what is? So the answer is correct. The answer is true. What happens in atomic layer deposition processes? We deposit materials, like we grow them in layer by layer. So if we have a starting surface, we will first allow some precursor A to flow through. So that precursor will react with our surface. Then after some time, we'll remove all the precursor A. So then we will flow precursor B. The precursor B will react with the adsorbed, like whatever surface molecules of a precursor A that are adsorbed on the surface. So it will form a monolayer of film. Then we will remove the precursor B completely. Then we repeat the process again. So this is how we grow the layer. So what we do here is we add one atomic layer over the other. So one great advantage of this process is that we can control the growth of the film very like finely. So we can so since it is in the word itself, it's atomic layer deposition, we are depositing it layer by layer. So it actually gives a film with minimum thickness, and also we can control the quality of the film very well in this case. So there are many there are several materials which can be deposited using the atomic layer deposition process. So some of them are aluminum oxide, titanium oxide, and so on. Okay. Is there any doubt regarding this?
What is the maximum thickness possible using ALD?
I think it may be in nanometer range, not higher than that. We cannot grow micron films. It will be like a few nanometers range. That's the maximum we can go.
Okay.
Less than 10 nanometer.
Less than 10. Okay. Okay. Thank you.
So next we'll move on to problem 8. So you want to fabricate a micro heater structure. You would have learned about micro heater structure in the first week, and insulated by silicon dioxide wafer. So only silicon wafers are available as substrates. Here is a list of fabrication processes. Make a sequence of the processes so the expected device can be fabricated. The list of processes are: first one is thermal oxidation, second one is metal deposition, third is lithography, fourth is PECVD of silicon dioxide. So PECVD is plasma enhanced chemical vapor deposition. So it is a deposition deposition method where we are depositing silicon dioxide instead of growing on the surface of silicon. So what we do is in PECVD we will pass the precursors, make it react, and then it will get deposited on the surface of the wafer. In growth, the growth starts from the silicon surface. Here we just deposit the material on the surface. So here we have 4 options. So which are the sequence of steps that will be involved? Before that, I'll just say if you are having a micro heater structure, so how will the cross you can say the answer first. What is the answer?
I think first is a thermal oxidation, then comes lithography and metal deposition and PECVD. I would go for C, possibly.
Okay. Okay. Thermal oxidation, then lithography, then metal deposition, and then PECVD.
Correct.
So this sequence is correct. So let's see. So what happens is, first we will take a silicon wafer. So the thermal oxidation process is mostly like in most places it's level 1 process. So level 1 means we should not have any metal or anything on the top. We need a pure silicon wafer, so that the like oxidation will happen at the surface of the wafer. So that will be the first step. So first we'll take a silicon wafer, then we will deposit thermal oxide on the top. Okay. Then we'll go for photolithography, where we will one question is, this lithography is for which process? Like what we do with the lithography?
That is for patterning the metal deposition.
Yes,
That is
correct.
the microheater deposition.
Yeah, correct. So we have a thermal oxide, then we will do like we will coat photoresist, and then we'll develop it so that we'll have a pattern. So this photoresist will not be hard baked, means it will be soluble. If you still dissolve in solvents, it will get solved, like it will get dissolved. Then we will go for metal deposition. So this is a photoresist. So we'll go for metal deposition. Metal deposition can be done either by sputtering or by using evaporation techniques. So here we'll have the metal that is deposited. Then after this we will go for lift off, a process called lift off, where we put this in the solvent. So the solvent will dissolve the photoresist. So the solvent will come like this, and it will see the photoresist and it will dissolve it. In the places where the metal is deposited directly on the silicon dioxide, like there it will remain. In the remaining places where the metal is deposited on the photoresist, they will get lifted off. So that is a lift off process. And then in order to insulate it, we will coat it with the we'll coat it with the PCVD silicon dioxide on top. So after this we will coat it with PCVD. So the correct answer is 1, 3, 2 and 4, option C. So now we'll move on to the next question. So piling bedworth ratio, silicon dioxide to silicon volume ratio, which we saw in the previous question, is given for as 2.19. So what would be the thickness of oxide film that has formed if 10 nanometer thick silicon has been consumed during the oxidation?
I just forgot to make a note of the expression.
Yes, I'll show it again. So these slides will be uploaded in a Google Drive. I'll share the link, and the video also will be shared. So this is the equation. Silicon dioxide thickness by silicon thickness is 2.19, which is 1 by 0.46. So we can I think we have what we need to solve. So the ratio is there. So we just have to know Vox by V silicon is 2.19. So what is the thickness of oxide film if 10 nanometers thick silicon has been consumed during oxidation?
21.9 D.
Yes. The correct answer is D, 21.9 nanometer. So now we'll move on to the next question. Problem 10. Yes. Any doubt?
No doubts.
Okay. So we'll move on to the next question. Problem 10. E-beam evaporation is a physical vapor deposition technique in which the target material is bombarded with an electron beam in a high vacuum chamber. Is this statement true or false?
It's true.
It's true. Yes. So yeah, there were other evaporation methods as well, thermal evaporation and e-beam evaporation, right? So in e-beam evaporation, what happens is, like we have a crucible with material. So we will have a crucible with our material that we want to evaporate. We'll have a substrate that is in line of sight of the crucible. Then we will have an electron gun. So here you can see that how the electron beam is generated. So we'll have a filament which we will be heating. Due to thermionic emission from the filament, we'll have the electrons coming out of the filament. We'll accelerate the electrons and also have a magnetic field in order to control the trajectory of the electron, so that the electron beam will fall in the target material to be evaporated. So once it falls on the material, it will start heating the target material, and so in this process what happens is, it's physical vapor deposition. We convert the solid phase directly into gas phase. So the material will get it will evaporate and it will fall on the substrate. So thus we deposit this metal on the substrate. So one advantage of this process is that if you see the thermal evaporation process, there you need to melt the metal, like you need to heat the metal to melt the metal. So your the melting point of your source should be much lower than your crucible. Otherwise what will happen is, when you heat both together, your crucible will also melt. So you whatever material your crucible is, that may also get deposited in the substrate, which we don't want. But in the case of electron beam, we can have a crucible which is not very high, not having very high melting point, but somewhat moderate melting point. We can selectively melt only the source material or the target material that we want to melt. And also in every evaporator chamber we'll have a crystal thickness monitor. So this is to we need to know at what rate the deposition is going on. So we'll use this crystal thickness monitor in order to find out what is the deposition rate that we are having. And another important thing is, let's say this is physical vapor deposition, right? So first we have to melt the material in the crucible, make it into vapor, then we have to allow the deposition to happen. So for that we may have some kind of blocking mechanism here. So we'll open this shutter at the time where we know that the material in the crucible has melted completely. Then at that time we will open the shutter, so that we'll have some normal or somewhat uniform deposition rate. So is this clear?
Yes.
So the next question is also related to evaporation. In E-beam evaporation technique, the current density leaving the filament can be formulated as, first option is Gauss equation, second is Maxwell's equation, third is Richardson's equation, and fourth is Faraday's law. So this was briefly mentioned in the course content.
I'm not sure. Richardson's equation?
Yes. So the answer is Richardson's equation. So how we generate the electron beam is similar to how light is produced using the incandescent bulb. So we will flow current through a filament. In the previous figure also you can see, right? We will flow current through the filament, and as we increase the current through the filament, like the temperature in the filament will also increase. So this is by Joule's heating effect, I squared R into T. So at a particular point, the electrons will have some energy to escape the surface. So but in the case of our electron beam gun, the electrons must flow like it should follow a particular unidirectional path. We don't want our electrons to emit anywhere, like in any direction. So we'll have an accelerator and also a magnetic field to control the trajectory of the electron. So like the way, so it is a thermionic emission, and it is defined using the Richardson's equation. So the answer is Richardson's equation for this problem. We'll move on to the next problem. In PVD, electron beam heating works by, so PVD is physical vapor deposition. A is generation of argon plasma, B is magnetic focusing of electron beam, C is resistive heating of filament. So what is the answer?
Generation of argon plasma?
No, this is electron beam right, heating. So this is related to E-beam evaporation. So in E-beam evaporation, we heat it using which mechanism? Earlier, I think in earlier question we saw that.
Is it resistive heating? No, it can't be, right?
It is like we are heating the filament. Resistive heating is what is causing the temperature in the filament to increase. Like, but at a particular point, the electrons will gain enough energy to come out of the filament. That is what is happening. Magnetic focusing is to like control the direction, like of the beam.
Okay, so that means
like how we like say if this question is like how we are heating the material to be deposited, then we can say maybe magnetic focusing of electron beam. But how we are generating the electron beam, then we can say it is resistive heating of the filament.
So which is a correct answer? Because according to me, electron beam is there, fine, but B as talks about the focusing. That is not the question
Yes.
being asked.
Yes. So like if the question is how the material to be deposited is heated, then like because we focus the electron beam to fall on the source, we can heat the material. So that will be like how we are heating the target material. So in resistive heating of filament, that is how we generate the electrons.
So I'll have to decode this as the way to generate electron beam.
Yes. Not like here we are not mentioning heating of the target material, right? We are not mentioning heating of the target. If it is heating of target material, then it will be like magnetic focusing of the electron beam. So the answer is C, resistive heating of filament.
Okay.
So next question is why is argon gas used during sputtering of a metal? Option A, it's an inert gas, so it does not react with the target. B, it bombards the target. C, it can be used as carrier gases for other gases required in the processes. D, all of these.
Answer A is an obvious answer, but looks like D is the answer.
Yes, so D is the answer. So what happens in sputtering process? So in sputtering, it is also a type of physical vapor deposition where we convert solid into vapor phase. Then we will allow this vapor phase to be directed to the substrate where we want to deposit. So that's how we deposit it. So what happens in the sputtering is that we will have the so here the cathode sputtering target is the material that we want to deposit. Let's say it is a metal, it can be gold, it can be chrome, it can be anything, and this is the substrate where we want the material to be deposited. So the what happen, we'll also have an argon ambient. So we will apply some voltage and we'll generate a plasma. This plasma is what, ionized gas. So and also one important thing is argon is a inert gas and it is also a heavy gas, means it has high molecular weight. So when it gets accelerated, it will hit the cathode material and it will cause some ions to be expelled away from the substrate. So these ions will get attracted towards the anode and they will get deposited on the substrate, and that's how the sputtering reaction happens. And also, let's say this is for metal sputtering. There is also another type of sputtering called reactive sputtering, where we will send some gas as well, oxygen or nitrogen. So when the sputtered ions come, like it can be made to react with the ambient, oxygen ambient or any ambient, to form a film that is deposited on the surface of the substrate. So another important thing is, when we are like say we want a metal to be deposited, we don't want any reaction to happen on the substrate. Our substrate should not react with whatever ambient that is present inside and form some other film. So whatever gas that we use, it also has to be inert. So argon is an inert gas. It does not react with the target. Then it bombards the target as well. It should not also react with the target to form some sort of other film on the surface. Then it can also be used as carrier gas for other gas that is required in the processes. So the answer is all of these, option D. Is it any doubts?
Yeah, that's correct. Okay.
So which is not a PVD? PVD is physical vapor deposition technique. A is ALD, B is E-beam evaporation, C is thermal evaporation, and D is sputtering. So what is the answer?
Is it ALD, which is not a
Yes, the answer is ALD. So in ALD, like we saw in one of the earlier slides, yeah, the answer is ALD. In physical vapor deposition, what we'll do is we will like use vapor to deposit something in the on our desired substrate, and we will use a physical process in order to generate this vapor, not a chemical process. So in the case of ALD, what we are doing is we are having some chemical reaction that is happening. So first we are flowing some precursor, then we are purging it, then we are flowing another precursor. So we are having like whatever film that is formed here is due to some chemical reaction between the two precursors A and B. So this is a chemical deposition process, not a physical process. In the case of sputtering, like what we saw earlier, what we do is we like give some energy to the argon ions, make them hit the sputtering target. So that is some kind of physical reaction. We are making the argon ions to hit the target with a lot of energy, and then because of that some ions from the sputtering target are released. So that is a physical process. So sputtering is also a physical process. Then in E-beam evaporation, what we are doing is we will heat the material using electron beam. Again here what we are converting the solid phase into some vapor phase which is falling on the wafer. So there is no chemical reaction involved here. So when this vapor reaches the substrate, so it will solidify and it will form a film. There is no chemical reaction. So whatever composition you have in your source, the same composition will be deposited in your wafer. In the case of thermal evaporation as well, we will use some resistive heating filament in order to heat the crucible. In this case, like we should, so since we are heating the crucible using a resistive filament, we should make sure that our crucible is having a very high melting point compared to the material that is being molten, that is being converted into some melt. So one disadvantage of this thermal evaporation process is that we cannot deposit all the materials. Let's say if we are having some like we cannot deposit material that is having very high melting point. Let's say it is tungsten, so it has a very high melting point. If we need to deposit tungsten with evaporation, then we'll have to have a crucible that will have even higher melting point than that tungsten, so that when we are evaporating, it will not fall on the, like it will not form any vapors of the crucible and or any other unwanted reactions. So in the cases of sputtering, e-beam evaporation and thermal evaporation, we are forming vapors using some physical processes. Means there is no chemical reaction involved. If there is some chemistry involved, then it becomes a chemical vapor deposition. So we don't see any like chemical reactions happening here. So the answer is ALD. Is this clear?
Okay, yeah.
So now we'll move on to next question. So this question is related to photolithography. Which of the statement is correct for HMDS? HMDS is so it hexamethyl disilizane. So option A is it is used before the photoresist coating to increase the adhesion of the photoresist. Option B is HMDS layer is generally very thick compared to photoresist. C, it is an agent that increases roughness of the substrate surface, increasing adhesion of the photoresist. D, it is used to change the optical property of photoresist so that photoresist can be exposed using light of another wavelength.
If there is no negative marking, I would like to go for D.
D?
D.
Okay. So in the photolithography process, you would have seen that the first step will be cleaning of the wafer, right? In the second step, there will be some adhesion promoter. Like sometimes in our substrate, the photoresist will not stick readily. So in that case, we'll need some adhesion promoter, something that will facilitate easy adhesion of the photoresist to a substrate. So in HMDS is something that is used as an adhesion promoter. So like it can be either option A or C, not D. And another important thing is we don't want we don't want to change the optical property of photoresist. So let's say most of the photolithography equipments, like they can be like they will have some particular wavelength which like they will use to expose. And let's say we want to like make the photoresist sensitive to another wavelength, like there may be some other kind of photoresist that may be suitable for that. Like we don't want to, and it is not easy to change the property like that. So option is like the answer can be either A or C. Which one do you think it is?
C.
The correct answer is option A. So one important thing is here it is what it is mentioned is that it is increasing the roughness of the substrate surface, increasing the adhesion of photoresist. So like when we are using any adhesion promoter or something, we don't want to affect our surface like substrate surface. Let's say we want to, it will alter the properties of like whatever device that we are making. If we make it more rough, then like it will not give us like we may not get good devices if our device is very sensitive to the surface. So even for transistors and all, let's say we are going for patterning gate oxide or something. Then if we like increase the roughness of the substrate, then whatever after gate oxide, if you want to deposit metal on top of that surface, then like the roughness will cause an issue when we are doing subsequent process as well. So whatever adhesion promoter we use normally should not affect the substrate. I mean, it should not affect the substrate in a bad way, and it also should be easily removable. So that will be one of the requirement for something to be used as an adhesion promoter. So it will just increase the adhesion of the photoresist. It will not make the surface rough. So this is the chemical formula for HMDS. So what happens is, so on the silicon surface we may have some dangling OH bonds. This will create some sort of strong adhesion, this will create this kind of bonds in the surface. So when we coat the photoresist on top, then their adhesion between the photoresist and the silicon surface will be strong. So before we coat the photoresist, we will also what we do is we do cleaning of the wafer, mainly solvent cleaning. Then we will dry the wafer, and we will do heating, we will heat the wafer at 110, generally 110 or 90 degree centigrade, in order to remove any moisture that may be present during the cleaning process. So when we do that, what will happen is the surface of the wafer may have, normally if you dip a silicon wafer in if you dip a silicon wafer in the water, you will be able to see that the surface is mostly hydrophobic, means the water will not stick readily to the surface. If you blow it off, it will easily come off. But if you have a silicon dioxide wafer, a wafer with silicon and some silicon dioxide on the top, when you dip it in water, what will happen is it will be hydrophilic, means the water will stick and it will form some sort of film on the surface. So this is due to that OH bonds. So what this will do is it will create this kind of bonds for the photoresist to come and stick readily on the surface. Is this clear?
Okay.
Okay, so answer is it is used before photoresist coating to increase the adhesion of the photoresist. Okay, next one is which of these sputtering techniques gives better yield? A is co-sputtering, B is DC sputtering, C is E-beam sputtering, and D is magnetron sputtering. So these are all different sputtering techniques. Which of these gives a better yield? And what is say sputter yield? So sputter yield is the number of argon ions, or so number of target atoms that comes for every argon ion that is bombarding the surface. So say in our target material, if we are having one Ar plus ion that is coming, then how many or we are having some n number of Ar plus ions coming, how many target ions will come out of the surface? So that is the sputter yield. So which of this sputtering techniques will give us good yield?
Can you please repeat what exactly was the sputter yield?
So sputter yield is the number of target atoms that will come out of the target for the number of argon atoms that is falling on the surface. So let's say we are having some n number of argon atoms that are bombarding my target. How many target atoms will come?
I would go for E-beam sputtering. C.
So that is wrong actually. There is no E-beam sputtering. So in sputtering, what we need is we are just hitting the target with some high energy argon ions. So if something comes with very high energy and hits, then some atoms will come out, right? So those atoms will be deposited on the surface of our substrate. So that is what is happening in sputtering. But electron beam, it has very less mass. It can get accelerated, it can get accelerated easily. But since it has less mass, even if it impacts on the substrate, it will not readily cause the ions to come out. Like it will not cause the target ions to come out readily. You understand that, right? E-beam evaporation is there, where we use the electron beam to heat the target material, make it evaporate, and then deposit. In sputtering, what we will do is we will just hit, we will accelerate the argon ions, make it hit the target. Due to the impact of this argon ions on the substrate, some of the ions will come out on the surface. So that is what is happening in sputtering. So E-beam, there is no E-beam sputtering as such, but there are other 3 options. Which one is the answer?
I think co-sputtering may not hold good because it requires 2 sources. That is ruled out. So either it has to be DC sputtering or magnetron sputtering. I think it is magnetron sputtering.
Yeah. So the answer is magnetron sputtering. We'll see in the next slide. So in co-sputtering, what we'll do is we'll sputter 2 kind of sources at the same time. So this can be used to generate any alloys. We can make any alloys by controlling the various process parameters. In the case of DC sputtering, what we will do is we'll generate the plasma with the DC source, and we'll make the argon ions accelerate. The argon ambient will be present here, so it will accelerate towards the target, and when it hits the target, it will generate some ions. These ions will fall on the substrate. So that is what is the DC sputtering. In the case of, here when we are just doing DC sputtering, we do not have any control on the path in which the argon ion moves, right? So when we are just accelerating argon ions, it can hit here. So it can whatever target ions are coming, it can move here, it can move here, some can move here as well. So they may get deposited on the walls as well. But in the case of magnetron sputtering, what we will do is we'll use a magnetic field in order to control the direction as well. So we will have more control over how the target ions are moving inside the chamber. So since we have better control over that, we can ensure that most of the target ions that are leaving can reach the substrate. So not only when we are sputtering, our argon ion should fall on the cathode, and also the target ions should come and deposit on the substrate. That also should happen. So if we control them using magnetic field, then we'll have better control and we'll have better yield compared to DC sputtering. Is this clear?
Yeah.
So next question is problem 17. The mask having dark features and transparent background is A. dark field mask, B. bright field mask, C. grey mask, D. black and white mask. So this is a question related to photolithography. So dark features means if this is our mask, we are having some features which are looking dark, and we are having a transparent background. So it will look like this. Any guess?
I'm not sure of the name. I think it must be bright field mask.
The answer is bright field mask. So in bright field mask, what happens is let's say we are making are you aware of the we can make a layout to make what kind of pattern we want to make in a mask. So let's say in my layout I am drawing this an eye. I am drawing this. In a bright field mask, whichever pattern that I draw in my layout will be there. So like in those regions the light will not pass through. There will be some chrome. If it is a soda lime mask, the remaining, this will be soda lime or glass, and this will be chrome. So this chrome material will block the light that is passing through this region, and in all the other regions it will be transparent. So that is bright field mask, where we have some small opaque region surrounded by large amount of transparent region. In the case of dark field mask, we will have more amount of opaque region and some small amount of transparent region. So light will only pass through this region. So we need light exposure to happen for like to change the property of our photoresist, so that we can make some pattern. So this is what happens in dark field or light field mask. So like you would have also been aware of the photoresist types. Like you might have heard of photoresist. There are two types of photoresists. One is positive photoresist and negative photoresist. So in positive photoresist, there are several like types of positive photoresist. Some of the AEZ like 4562, 5214E are some of the examples of positive photoresist. There is also S1813, that is also a positive photoresist. Some of the negative photoresists are NLOF, so they have some series number like this. So these are some of the like readily available photoresists that are sold. Here like we have these last two digits, right? So that will tell us how much thick the photoresist is. Say this if we are having S1813, if we code the photoresist as per the standard parameters that are given as per the data sheet of the photoresist, so they'll have some certain amount of time in which they have to spin the photoresist, and certain speed at which the photoresist like should be spun. So that one, if we do at that parameters, then we will be getting the thickness of the photoresist which will be given by the last two digits. Is this clear? So also, like say in deposition process, like if you want to coat a photoresist, what happens is we'll take a substrate, we will dispense some photoresist on the substrate, then like so this substrate will be held by using some sort of vacuum in like in a system. So after that we will input the like spin duration as well as the spin RPM. So depending on the duration and the RPM, we will start to spin this. So what will happen is the centrifugal force will cause the dispensed photoresist to spread across the substrate. Once the coating process is done, we will have somewhat the photoresist would have deposited across the entire wafer surface. So that is what happens. So there are like since these are chemicals which are sold by some of the companies, they will have some standard parameters regarding the rate at which the spin happens as well as the duration of the spin. So if we follow those parameters, the desired amount of thickness that we will get will be normally given by the last two digits. So if it is 4562, if we spin at a particular like spec that is given by the manufacturer, we will get around 6.2 micrometer thick of photoresist. Again 5214A, we will get 1.4 micrometer thick. So this is one of the spec regarding the photoresist. Same will occur in the case of negative photoresist as well. So like what is positive photoresist and negative photoresist? So positive photoresist are like certain photoresists. These chemicals like if they are exposed to some sensitive light of particular wavelength through which they are exposed, the exposed regions will dissolve easily in the developer. So any bases we have, it will get dissolved easily. But in the case of negative photoresist, the region that is getting exposed will polymerize and it will harden. The remaining region that is not exposed will get easily dissolved. So here what we have is we have a mask and we have some dark region as well as some transparent region. So this dark region is where chrome is present. In the transparent region we just have glass. So chrome is there on like when light falls, it will fall through the transparent region, it will not fall through the opaque region. So here like this kind of shading, the light does not fall on the photoresist, and in this kind of shading the light falls on the photoresist. So what happens is, in negative resist, wherever the light is not falling, it will like kind of polymerize and it will harden. But where the light is falling, in the case of negative photoresist, what happens is, where the light is falling, it will polymerize and it will harden. But the remaining regions which does not have the exposure of light, they will remain as such, and if we put it in a base, then they will get dissolved, and we will have a pattern where the regions that are not exposed to the light will remain. Is this clear?
Okay.
In the case of positive photoresist, what happens is, the light that like whichever region is getting exposed will be easily dissolved. So those regions will get removed quickly. So this region, so this is there is one mistake here. So this is the positive photoresist and this is the negative photoresist. Okay. So what happens is, wherever light falls, it will get dissolved. So wherever light falls, it will get dissolved. Then we can transfer the pattern to the substrate. In the case of negative photoresist, what happens is, wherever light falls, it will remain insoluble. Wherever light does not fall, it will get dissolved. Sorry for the confusion. So in the case of I'll repeat this once again. In the case of negative photoresist, if light, this is the region where light is being blocked. So if light is falling in all this region, wherever the light is getting exposed, those region will harden. Wherever the light does not fall, that will it will retain the earlier property and it will easily get dissolved in the base. So what happens is, when we do development, we will have photoresist remaining in this region, in the case of negative photoresist. Then if we do etching, if we have a layer below this and if we do etching, then we can when we are etching, we will the plasma will get exposed in this region. So we will etch this region and the pattern will get transferred to the underlying film. So this is what happens in a negative photoresist. But in the case of positive photoresist, what happens is, wherever the light is exposed, say here we are having some opaque region, wherever light is exposed, it will become more soluble to the developer. Wherever light is not exposed, it will remain insoluble. So when we do development, this pattern will remain insoluble. So this pattern will remain insoluble and the remaining pattern will get dissolved. Is this understood?
Yeah.
So next, as we saw in earlier question, we have two kinds of mask. One is bright field mask and dark field mask. So in bright field mask, there is some chrome metal which is opaque and it is surrounded by clear region, and in dark field we'll have some opaque region. In we'll have some regions where there is some regions which is transparent. So if we just say take cross section of that, we'll get something like this. So depending on what combination of mask and photoresist we use, we can have different kind of patterns. Let's say we are having a negative photoresist and this is our bright field mask. So in our bright field mask, the light does not fall through this region, it will fall on this region, right? So wherever light is exposed, the photoresist will remain in negative photoresist. So we will get this kind of pattern. In the case of positive photoresist, what happens is, wherever the light falls, the resist will get dissolved. So we will get this kind of pattern. In the case of dark field, if you are having a dark field mask, then wherever light falls, the photoresist will remain in the case of negative photoresist. And similarly in the case of positive photoresist, wherever light falls it will get dissolved. So this is so by using the same photoresist but with different kind of mask, we can have different kind of patterns. So like by using suitable combination we can choose like what kind of pattern we want for the same mask. Is this clear?
Okay.
Any doubt?
No, not at this point.
Okay. No, like say mask is like we can make mask one mask at a time, right? A mask is like kind of permanent. Let's say we want to do a patterning which is like we have drawn a mask like this, but we want to expose the region that is in this eye shaped. We want to create a pattern where this eye shaped region is getting exposed. So then we can use a different combination of photoresist so that we'll get the desired pattern. So that is what in like I wanted to convey in this mask and photoresist combination. Okay. So now we'll move on to the next question. The class number of a clean room denotes what among the following options? A. The pressure inside the clean room. B. The number of people permitted inside the clean room at a given time. C. The lifetime in years.
D.
Yeah, D. So the number of particles per cubic feet allowed inside the facility. So there are various classes, class 300, 1000, 10,000 and so on. So depending on, so class 100 will have very less number of particles per cubic feet. So most of the if you see in a clean room, the lithography process which is very critical, and it should have like the room should not have much particles, so that will be having the lowest class in a clean room in general. So next question is in the deposition, PVD stands for A. Physical volatile deposition, physical vertical deposition, physical vapor deposition, both A and B. The answer is
C.
Is physical vapor deposition. Okay. So next is problem 20. Here transfer of a pattern into a material after deposition in order to prepare for etching is called A. Etching, B. Patterning, C. PVD, C. CVD. CVD is chemical vapor deposition. It is a similar process to that of a physical vapor deposition. Only thing is the reaction happens in a chemical manner.
It has to be patterned first. So
yes,
it is
so
pattern.
transfer of a pattern is
Patterning.
Yes, it is patterning. Like say if I change the question to transfer of a pattern into a into the deposited material is called after if we are transferring the pattern into a deposited material. Let's say we are having a thin film. If we want to transfer the pattern to the thin film, then what process will we use? This is a photoresist.
Etching.
Then we will use etching. Okay. So now we'll move on to the next question. Dipping substrate into chemical solution that selectively removes material is called?
It's wet etching.
Wet etching. So in dry etching, what we'll do is chemical reactions happen, but they are in the vapor phase. Normally in the vapor phase, or we can also in this dry etching also we can use argon ions to remove the. We can bombard the substrate with argon ions and remove the material. In wet etching, we will dip the substrate in a some chemical solution. So here you can see we'll dip the substrate in a chemical solution, and the etching will happen depending on the chemistry between the whatever chemical we are using. So one thing is, do you know what is isotropic, anisotropic?
Yes.
So in isotropic, the etch rate will be same in all the directions. In anisotropic, we can control the we can control how much etch. The etch will not be uniform in all the directions, so we can get this kind of profile. Or in case of dry etching, we can also get this kind of profile for anisotropic etching. In the case of isotropic etching, we will get something like this. So here like how much it has etched in the lateral direction will be the same as how much it has etched in the vertical direction. In this case and this case we can control so that there is more amount of vertical edge compared to the lateral edge. So in the case of dry etching, there are like two types of dry etching that we can use. One is we can just have some inert gas plasma like argon ions to bombard on the surface and remove the material physically without any like chemical reaction involved. And also we can also have some reactive gas. So this also is in a plasma. It will react with the surface, and by the chemical reaction it will first it will get absorbed on the surface, it will react with the surface, it will form some volatile products, and those volatile products will be removed from the surface. So these are like two kinds by which dry etching can happen. So in wet etching it will just react, only chemical reactions happen, there is no physical phenomenon. So we'll move on to the next question. What is lithography? A. Process used to transfer a pattern to a layer on the chip. B. Process used to develop an oxidation layer on the chip. C. Process used to develop a metal layer on the chip. D. Process used to produce the chip.
Transfer of the pattern.
Yes. So the correct answer is transfer of the pattern. So lithography means like writing on stone. So it involves drawing some kind of pattern. Next problem is DC sputtering cannot be used for insulating materials. So like you would have learned about different kinds of sputtering. So in that like in DC sputtering like, can it be used for insulating materials or not? Is it true or false?
It's false. It can't be, then it is true. Yes,
it is true. DC sputtering cannot be used for insulating materials. So what happens is, like say in the case of DC sputtering, we will just apply some DC voltage between the two, between the substrate and the cathode. So this cathode will be let's say it is of particular charge, negatively charged. Then like when the argon sorry, this will be positive like what will happen is this will be this side will be negatively charged. So the argon ions will fall on the cathode, then it will emit some sort of target ions from the cathode. These target ions will be positively charged, so they will get attracted towards the anode, and that's how the deposition happens in DC sputtering. So this DC sputtering technique is suitable only for metals, not for insulators. But there is another kind of sputtering called RF sputtering, where we give some kind of alternating voltage that is superimposed on DC voltage. So it is not just AC voltage, it will have some DC offset as well. And the frequency of the AC voltage is around 13.56 megahertz. The main reason is like if you see most of the clean room fabrication tools, the RF frequency will be around 13.56 megahertz. It is to avoid any interference with other communication frequencies. Then what happens when we do like DC sputtering of insulator? So what happens is if we are having an insulator like this, which is our target, then when we are giving negative voltage here, the negative ions like the negative charge will be formed on the plate here, and since it acts like a capacitor, positive ions will be formed here. So argon ions have to be attracted towards negative charge. For like if there is positive charge here, then repulsion will happen, it will not get attracted towards the substrate. But if we have a RF sputtering, the voltage will be alternating. So at one point it will be negative, and at other point this will be at positive voltage. So when this is at positive voltage, at this side the charges will be negative. So at that point the argon ions will get attracted towards the silicon dioxide substrate, and then it will sputter, like silicon dioxide atoms will come out. Then in the next phase what happens is the polarity will change from positive to negative, right? So when it becomes negative, then the argon ions will get attracted towards this the wafer. But what happens is this happens at a frequency of 13.56 megahertz, which is a very high frequency, and argon ions are also very heavy. So like they will get attracted towards the substrate, but they will not move fast enough within that cycle so that they will hit the substrate. So they will start getting repelled towards the substrate, but once they have moved some distance, again the polarity will change to positive. So it will again get attracted towards the sputter, the target. So that is what happens. So but the electrons will get it will move towards the substrate, and it will move easily between the substrate and the target material. So that is what happens. Is it clear?
Yeah.
Any doubt?
No, I don't think I have any doubt.
So another important reason why we are using argon ion is that it is inert, and also it has a larger mass compared to other inert elements. It's also we can use it has a larger mass, so we will be able to give more amount of force that is bombarding the substrate, that will help us to release more amount of atoms from the silicon dioxide surface. So next problem is, which gas is used to dry the wafer? Argon, nitrogen, oxygen, all of the above.
Argon.
So the common gas, argon can also be used, but mostly we use nitrogen to dry the wafer. One reason is that first it is inert, and also it is relatively cheaper compared to argon. It is easy to afford compared to argon. So after we do any solvent cleaning or cleaning of the wafer, then dipping the wafer in deionized water, then in order to remove the water from molecules from the surface, we will use some nitrogen gun, or we will pass a stream of nitrogen over the wafer in order to push the water molecules away. So also if we use argon, let's say we are giving it at a very high force, like in plasma or something, then it will damage the surface. But for drying purpose, the force will not be that great. Next. So next problem is problem 25. Positive photoresist polymerizes and hardens when it gets exposed to the correct wavelength. True or false?
False.
Yes. So it is false. So negative resist is what polymerizes and hardens. So so photoresist is composed of many compounds. It has some polymer that will be dissolved in some solvent, and also it has some sensitizers. Since the photoresist has to be sensitive to particular wavelength of light, so it will have some sensitizers as well. So the solvent, we will have a solvent so that the photoresist will be in a liquid form. So if you see the process in which we transfer a pattern to wafer, the first will be cleaning the surface of the wafer. Then we will do dehydration bake. So dehydration bake we will do using hot plate. This is to remove all the moisture from the surface, so that there is no moisture left. Then we will do spin coating of the wafer with photoresist. After spin coating, we will do a soft bake. So in soft bake, generally it is done at 110 degree for 1 minute. So this is done to partially remove the solvent, not to remove the solvent completely, to partially remove the solvent, so that it will become some more thick. It will not be like a liquid on top of a wafer surface, but it will be somewhat little bit solidified. and also it will be more sensitive to the light that we expose. So after soft bake we will proceed with exposure. Then what happens is, after exposure, the regions which get, if it is a positive photoresist, the regions which get exposed will get dissolved readily in the developer, so which is a base based developer. Then once we finish development, we'll again wash it with lots of DI water in order to remove the developer. So in most of the cases, DI water is deionized water that acts as a stopper for the developer reaction. Then we'll, if we want to go for etching, we will do another dehydration hard bake. So this is to completely remove the solvent from the photoresist. This will be done for longer time, typically 3 minutes in some cases, or even higher, and it also depends on the photoresist spec. It will be given in the spec sheet. Then we can proceed for etching. Otherwise, like the photoresist will be soft, so when it gets exposed to plasma, or in the case of chemical etching also, when it gets exposed to the various chemicals, it will like easily get it can get peeled off, or it will get damaged, so that the etch will not happen in the desired region, it will happen in undesired regions as well. But if we want to deposit a pattern, any metal on the surface, then we will not do any dehydration bake. We want the photoresist to be still soluble in the solvents, so we'll just go with metal deposition. Then we will remove the photoresist by dipping it in solvent by the process called as lift off. So if we want to etch a metal, then we can, like if we want to do any etching process, we will do the dehydration bake to solidify the resist. Otherwise we will not solidify the resist. So this is a general process flow in which, like how we process the wafer. So yeah. So this we saw earlier. That's all. Any questions?
That's all.
Okay. Any so every week we'll be having this session. Any doubts or any feedback?
Not much. Maybe the